very much indeed, John, and thank you to all of you for turning out tonight on a unfortunately damp September evening. I'm really delighted to be here. This is a real privilege for me to join you and to share a little bit about my passion for chemistry, and hopefully give you a little bit of interest on areas of relevance and things that might be of interest to you. So, let me just, I should know my way around this really, but okay. So, I guess starting off just a little bit about why I became interested in chemistry. Chemistry is a somewhat abstract subject, and everything's very small and you can't really see it. But I guess there were a number of things that were important to me as a youngster growing up, and I know there are some young folks in the...
Sorry, Joe, could you like close to your mouth?
Yeah, okay, sorry.
Perfect, yeah.
People don't usually ask me to speak. So, chemistry for me was about trying to understand, it helped me to understand the world around me rather better, and that became really important because I could begin to rationalise what I was seeing and why it was happening, and of course that's a key part of chemistry. I loved doing experiments. I loved trying things, seeing what happened, and then trying to figure out what was going on, and work from there. So that experimental side was definitely something that struck me. I think it's a beautiful discipline. The aesthetic beauty of molecules and materials, and looking at crystal lattices and so on. What's not to like about all of that? And again, the idea that you can build these molecules up from the smallest particles, the smallest building blocks, on an atom by atom basis. And again, the creativity, the problem solving, and the discovery. And I think these are words that are important for chemistry. I often hear people saying, well, we know everything there is to know about chemistry. I honestly think there's nothing could be further from the truth. We've got a lot of new things to learn, and these things are going to be important for us as we move through the years, and as we try to tackle some of the challenges that are facing us as a society on a global scale. And so that brings me to the final point, why chemistry? Well, I believe chemistry is a force for good that will help to make the world a better place. And I want to share a little bit about that this evening. That's my perspective on why chemistry. I like this quote from Caroline Bertozzi, who was one of the 3 people last year who won the Nobel Prize for Chemistry. She was being interviewed conveniently by Chemistry World, which is, of course, the magazine that those of you who are members of the Royal Society of Chemistry will have land in through your letterbox once a month. I like the quote here, and then chemistry really caught me, especially organic chemistry. Well, we might need to differ on that, but that's okay. I just thought it was so inherently logical and beautiful and visual, and it really came to life for me. And I think that really is something that resonates very strongly with me, that it is the beauty of chemistry and the logic and so on that goes with it. So I thought that was a nice quote from somebody who's done rather well over the years. A little bit about the Royal Society of Chemistry. So the purpose of the RSC is absolutely to help the chemical science community to make the world a better place. So that's really the purpose of the organisation, and chemistry really does. Chemists and the community have really important contributions to make, and have made really important contributions. If we think just over the last few years, obviously with the COVID pandemic, the contribution in terms of developing vaccines, and beyond that then medicines, diagnostics, energy storage materials that in order to help us make that transition from fossil fuels into better and renewable technologies. These are important contributions, and chemistry is not the only discipline, of course, that's working in this space, but chemists are really important here. And I think there's an exciting future for chemistry and for young people coming into the discipline as we go forward. And that's, by the way, why I really like going out and speaking with youngsters in schools and so on, because I sometimes think it's difficult to connect, what's chemistry really about? And hopefully some of these topics resonate and help young people to see the possibilities that lie ahead for them. The Royal Society of Chemistry has a long history that dates back to 1841, and in 1841 there were some 77 chemists from many different areas of chemistry with very different interests came together in London. As I say, they had very different backgrounds, but the thing that they had in common was that they felt that chemistry had the potential to be a force for good and indeed to contribute to improving the world. And we hear a lot of the challenges around chemical waste and so on, fossil fuels, all of these things which are important and serious challenges, but the world wouldn't be the world that it is without chemistry and without all of the fantastic inventions and developments that have come over the years. So, as I say, it dates back to 1841. They formed the Chemical Society of London, and the Royal Charter was granted in 1848, and you can see the timeline, a few different incarnations, and finally the Royal Society of Chemistry, so the amalgamation of various institutes and so on, in 1980 to form the RSC. So from quite humble beginnings, from people who were determined to try to come together to work as a community and use the chemistry, the RSC now is a worldwide renowned organisation with over 50,000 members, and it really does connect up internationally. Many members in the UK, but also distributed across the globe, and that international global connection is really important to the society. The photograph, of course, is our first president, Thomas Graham. He was a very famous chemist in his day. He worked on dialysis, he worked in diffusion of gases, and he was one of the former inventor or discovery, really, of colloids and colloid science. So, really important contributions all that time ago. So, a little bit then about, what does the RSC do? What's it about nowadays as we think about the world that we live in now? So this is my slide. I just threw up the things that I thought were important to me as a young person, once upon a time, a young person coming into chemistry, but also working with young people. And it's one of the joys of working in the university, is having that opportunity to hopefully motivate and help to guide young people to achieve their potential and hopefully come out as really strong chemists. So I'm not going to say the first one yet again, but certainly the important role of chemistry in tackling the global challenges. And I'll say a little bit more about that. A lot of work around supporting, it's all about the community. It's a membership organisation, professional body, but the community is really important, and supporting and mentoring young people, developing over their careers. And these are things that, I joined the Royal Society of Chemistry as a student some few years ago, and it's always been an important part of that, of the organisation, and being part of the chemistry community for me was really important, because it sort of felt like a family, that people had similar values, similar interests, and I also really valued the support that I received from members when I was a young academic. The RSC does a lot of work in the areas of policy, influencing, so talking to ministers, civil servants, and other policy makers around campaigning for example, recovery of precious elements from electrical waste. These are important things that we need to be thinking about. We don't have endless supplies of some of the elements that we use in our everyday lives, in our mobile phones and our tablets and PCs and so on. So actually thinking about what happens to these at end of life. So the RSC, that's one example that the RSC's campaign to encourage people to be more aware of the the limited supply of these materials, and think about how we can help people to make their contribution. And I do believe that there are things that we need to do at national and international level which are really important, but there are also things that we can do as individuals that help to make things more sustainable. Of course, professional standards and accreditation. The RSC also has a wide range of journals, and so all of that dissemination of knowledge is really important. Finally, an area that I think is really important, and something I've really been trying to champion in my term as president, is the education activities of the RSC. And again, I'll touch a little bit more on that as we go through. Many of our members are in academia, but many more are actually in industry, and of course distributed into lots of different small, medium and large industries. But supporting innovation has been an area that the RSC has been working closely with our industry partners in terms of trying to understand and help to articulate to government the challenges of translating new innovations in chemistry into that valley of death, to get across to the point where the technology that can be rolled out and be developed companies and so on. So this particular report is about the challenges around the cost of putting chemicals and processes through full testing to make sure that at the time an investor might be confident enough to invest, the data needs to be there for them to do that, and that often requires significant investment at the front end. And so, trying to support the community by influencing policy around that area has been really significant. The other area that I would like to touch on is the emerging technology competition, which runs annually. It's been running for about 11 years, and this is where chemists and chemical scientists more broadly bring together their innovations, new things that they've developed in their labs and in their collaborations and so on, and they see a market opportunity, and they get mentoring, and there's they get investment and so on, and it's been an incredibly successful operation. In fact, we have my own department in Southampton. We've got a spin out which is Reid CO2, which is capturing CO2, carbon dioxide, and using that to create renewable polymers, and that's one example of a company that's come out of the emerging technology competition. Of course, through the creativity of the chemists and the others involved in the company, but the helping them get across that next hurdle is really important. The RSC, like many of us, are committed to trying to tackle the 17 Sustainable Development Goals, and trying to make sure that we make our full contribution to these areas. And many of these say chemistry loud and clear, but I think all of them involve chemistry at some level, whether it be the obvious ones of better health, new energies and so on. There's clearly a strong link to chemistry, but some of the others are maybe less directly obvious, but they're equally important. And part of course, many of the people who suffer most from the challenges in our society are not people that live in the Northern Hemisphere. They're often people in the global South, and they experience the most extreme consequences of the problems that we face, and yet they've probably not created these problems, and they're also not readily equipped to tackle them. So it's really important that we work together, and that's why the global reach is really significant. And so I just wanted to mention the Commonwealth Chemistry Federation. The Royal Society of Chemistry initiated that in 2018, I think it was, and that brings together a federation of chemical societies from across the Commonwealth countries, many of which, of course, include countries in sub-Saharan Africa and so on. And I had the pleasure of being at the first in-person Congress earlier this year in Trinidad, and the atmosphere supporting early career researchers to collaborate and build programs, partner to tackle the Sustainable Development Goals was really inspiring, and I think that gives me encouragement for the future, but there are challenges along the way, and we must keep working on that. So one of the areas that the RSC is very active is in championing sustainability and really trying to make sure that chemistry can make its full contribution. And of course, again, this is not something that we will do as chemists alone. There are very few things that scientists do alone nowadays. All of these are done in collaboration with other sciences and engineering disciplines and social science and so on. But a survey recently of researchers in chemistry showed that about 99% of research that's going on, the researchers really believe that the work they're doing has the potential to make a positive contribution to one or more of the SDGs. And again, I think the relevance of that is important. And we must work with partners in other countries with different experiences and try to make sure that we can get the influence in government and so on to try to move things forward. And I won't reflect too much on the discussions of last week in Parliament, but anyway, that's maybe for a chat over coffee afterwards. Another area that's really important and I think is crucial for the future of chemistry is the overarching inclusion and diversity piece, which has been something that the RSC, I really believe, is leading on internationally. I mean, I've had, as I say, the pleasure of visiting partner organisations around the world over the last 12 months or so, and everywhere I go, people tell me how valuable it is to have the data that the RSC has produced, providing the evidence in support of inclusion and diversity. And the images here are some of the reports that have been produced. They're all available on the RSC website. Anybody can have a look at them. But I think the two things are important. One is it's a whole community thing. It's about making sure that we're drawing on the best talent wherever that talent sits. And that doesn't happen by osmosis. It happens because you take some positive actions to ensure that there are people that, if a few years ago the Breaking the Barriers report about the lack of women in sorry, my brain's switched off for the night. It's obviously time to. Sorry. The Breaking the Barriers was about the advancement of women in academia, and you look at the key thing is that, of course, if all you do is give anecdotal information, you can always argue anecdote and say, well, but I know so and so or such and such. But the important part of it is having the data that sits behind it, and that's something I think the RSC does very well. To gather the evidence that provides the basis for then trying to make change. And in the Breaking the Barriers side, I think there has been significant progress in the last 5 years or so. The data show that, but there are other areas. The missing elements report, the fact that in the UK there's only one black professor in chemistry is a little bit of a surprise, and probably isn't representative of course it's not representative of the community that we live in. And so there's some reason why these things are happening, and we need to get to the bottom of that. And one of the things that the RSC's done in this space is set up a race and ethnicity unit with a significant amount of funding to pilot various programs, bringing young people through from black and minority ethnic backgrounds, giving them mentors in industry, mentors in academia, and they're seeing people that they always say you can't be what you can't see, and there's no doubt that these young people are benefiting from the opportunities. Last, I think it was probably May, I was in Manchester and met up with some of the people who went through the programme, the Broadening Horizons programme, in the first cohort, a number of them have already been offered jobs at the companies that they were seconded to and had their placements in. So by no means problem solved, but it's an encouraging start, and what it's doing is encouraging others to come into the companies to invest in this. It's not a problem just of chemistry, it's a problem of science in general, and whatever we learn along the way will translate elsewhere. And I was really pleased to see the Royal Society just a week or two ago announcing the launch of fellowships for young scientists, early career scientists from black and minority ethnic backgrounds, specifically to give them a chance to apply for these. It's still about excellent science, but it's trying to take some positive action to shift the dial and help to take this forward. Education is a really important part, as I said, and an area that I think, for me, it's the future of chemistry lies not in our hands, not in my hands, but in the hands of the young people coming through. And so the RSC has a whole website dedicated to resources for teachers, lesson plans and training opportunities and so on. And if there are any teachers in the room here that don't know about the resources, then I'd encourage you to have a look, because I think and there are many other, as I say, development programs and so on to try to help teachers to be able to get further their own personal professional development. Career support more generally, again, it's important for our community that we, you don't know everything when you get to the end of your A-levels or your degree or your PhD. It's a lifelong thing, as we all know, and the career opportunities and support that's in the RSC, I think, is really helpful. And again, this website down here captures a lot of that information. It also, gives profiles of chemists and people in lots of different roles. One of the hard things to describe about chemistry is, what do chemists do? They do many different things, and trying to capture some of that in profiles of individuals is really helpful. So that's really a quick whistle stop. I hope from the RSC point of view that it touches on some areas of things that are going on in the world around us that matter to you, and hopefully the actions that the RSC and others are taking by working together, by influencing and so on, that will help to make some inroads into improving these. Now, I am happy to pause if that's, I don't know whether anybody has any questions, particularly on the RSC related stuff, or whether I'll just hop on to a little bit of research. Keep going and get on with it. I've got it. Okay, so it's a nice opportunity also to say a little bit about some of the research that my group and my collaborators have been working on for the last few years. And I'm going to start by saying we didn't come into this area with a deliberate, there's an area we're going to work in. Like most things in chemistry and science, we stumbled across an interesting observation, which I'll say a bit more about. And as we kind of mulled that over, it became a possibility that we could exploit that and take it into a new area for us at least. So I'm going to talk about, I'm not going to talk about that. I'm going to talk a little bit about using metal complexes as, I call them, scaffolds, so units through which we can bind radiofluorine. But before I do that, just sort of explain some of the terms that I'm going to use. I appreciate that not everybody in the room is a chemist, and I hope I can help to sort of explain some of the concepts. And forgive me if it's really obvious, but humour me anyway. Okay, so metal complexes and coordination chemistry. So, getting carried away here. So first of all, a metal ion is a usually electropositive, usually positively charged ion. It's an electron pair acceptor, and so it will want to bond to other species that will provide these electrons. So it's usually referred to as a Lewis acid. And the counterpart, the bit that's going to bond to the metal, we usually refer to as a ligand. And the ligand L is usually neutral or maybe negatively charged, but it's going to have some electron density that's available to push onto the metal to form a compound from that. And so that would be our Lewis base. So we've got a Lewis acid, Lewis base combination. So metal ions don't go around on their own, they always go around with some groups bonding to them. That gives them additional stability, but that also gives us a picture in our minds of the sorts of molecules that we're dealing with. So when we combine a metal and a set of ligands, we make a metal complex. I think I've got, so we've got a little Ml6 ion here on the top right. So the metal is in the middle here, and then we've got 6 ligands surrounding. 6 is a good number. Most complexes have 6 ligands, 6 donor groups around them. Not all of them, but many of them do. Okay, so we can make our ligands a bit more complicated. We can link the atoms that are going to bond the metal together. And if we have more than one point of attachment, then we get more stable complexes. And that's important for some applications. Sometimes you want reactive molecules, sometimes you want them to be more stable. For the purpose of the work that we're interested in, we need stability. I'll explain a little bit more about that in a moment. But I think the important thing is that both the metal ion and the ligand affect the chemistry. And so as we combine an almost infinite number of possible combinations, we're going to see different electronic distribution across our molecule. That's what will determine the properties of the molecule, the colour, the structure, the reactivity, the stability, etc. And that's going to be the molecule that we're going to use for whatever application we're interested in. Of course, I'm just focusing on one today. These new molecules reveal new behaviours, and from these new behaviours comes new chemistry. And that's I would say, the discovery part of chemistry. I'm talking about metal complexes here. These could be organic molecules. It doesn't need to be metals, but different combinations are going to behave differently, and we certainly don't know everything there is to know. And with the techniques that we have available now, we can push the boundaries further than we maybe ever could in the past. So that's an interesting place to be working. I want to just introduce one family of molecules, and I've turned to my prop here. Some of my favourite molecules, as some of you in the room will know. So macrocycles. Macrocycles are just cyclic ligands. This is an example. So the yellow atoms in this model are we call the heteroatoms, the atoms that are going to bond to the metal and create the complex. And then the black and white atoms are carbons and hydrogen. So they're organic molecules with sulfur or nitrogen or oxygen or something in the ring that are the metal ion will then, too many gadgets, the metal ion can then bind in the centre of this. So this is the kind of donut or bracelet that's going to sit around the metal ion. And the key point is that not going that way though. The key point is that these metal macrocyclic complexes, when we put a metal into a macrocycle, we typically see significantly increased stability. That stability is going to be important for the applications that we're interested in. And there are many other applications of these sorts of molecules, which I won't touch on today, but the figure at the bottom is, so this is an oxygen-based. The red atoms are oxygens, so these are called Kraut ethers, and the purple atom is a potassium ion, which is sitting beautifully in the centre of the ring, makes the compound much more stable, and that's what you can then exploit in terms of the chemistry. So that's some of the terms that we'll see some of these species cropping up, but I just want to introduce this idea of why are we interested in binding radiofluorine to our metal macrocyclic scaffolds. And the reason for that is that fluorine 18 has nuclear properties that make it extremely interesting for a particular type of medical imaging, in this case positron emission tomography, so often referred to as PET imaging, and if you put that into Wikipedia or into Google, it's very confusing. Lots of pictures of dogs and cats and all sorts of things. But, PET imaging. Okay, so the point is that that fluorine 18 is a positron emitter. So the positron is a beta plus particle. It's the antiparticle of an electron, opposite charge, and about 97% of the radioactive decay from fluorine 18 produces these positrons. That's good because if you're going to use a radioisotope in nuclear medicine, you don't want lots of different types of processes going on, because if you're trying to do something with PET imaging and you've got different alpha emission or something, then that's going to give you some problems. So actually controlling the thinking about the radioactive decay is really important. It's ideal, many of the properties are ideal for PET imaging applications, and it's also a non-invasive technique. Typically the patient going to have a PET scan would have an injection intravenously, a small amount, very, very small amount of the radioisotope, and that will then move through the blood flow, move through the system, and then we can use the information from that. The half-life, the time for half of these fluorine 18 atoms to decay, to lose their positron, is just under 2 hours. So what that does is gives a little bit of a sense of how long you've got from generating the radioisotope until you need to be imaging a patient or everything's made and finished. So that 2 hour window, what that really means is you've probably got about 5 or 6 hours, maybe even a little bit more, in total from generation of the fluorine 18 to imaging the patient. So that's a bit of time for transporting the fluoride, doing the synthetic chemistry, making sure the molecule is what you think it is, because you need to make sure that obviously the regulatory bodies require that these are very carefully tested. So that's some of the important characteristics, but about 95% of all PET imaging, all positron emission tomography images that are taken in the clinic use one particular molecule. This molecule here, which is it's a fluorinated glucose molecule. So glucose is just a sugar. And what we can see here, so in the animation here, the yellow atom is a fluorine. It's replacing an OH group that would be in the sugar molecule itself. So it's a very simple transformation. So the vast majority of images that are taken use FDG, and that's because it's produced in many laboratories. There are other examples of some really nice chemistry developing different carbon fluorine 18 molecules, more sophisticated, but organic chemistry often requires multiple steps, multiple purifications, and the other challenge with carbon fluorine compounds is that often the carbon fragment isn't tolerant of water. And the fluorine 18 is generated in water in a cyclotron. So if your molecule you're trying to introduce it to doesn't survive water, then you've obviously got a drying process. All that's going to take time. It's difficult. So it presents some challenges. Having said that, there are there's some really nice chemistry in this area. The other problem with these, a lot of the carbon-based compounds, is that they're not really capable of tolerating sensitive biomolecules, and I'll just explain a little bit more about that in a moment. So the point is that if you want to detect early onset of disease, whether it be cancer or some heart disease or any other disease or tissue damage in a patient, ideally you would like to be able to inject the minimum amount of the radioisotope with its scaffold to carry it around, and then be able to target that directly to the organ of interest. And the problem with FDG, with the glucose molecule, is that it is a glucose molecule, and any part of the metabolic process that processes glucose will take up that molecule. So the process, the positron emission process, is shown in the diagram here. So you have your fluorine 18 species. It's then generating the beta plus particle and produces oxygen 18. So that's also a favourable aspect of fluorine 18. It's not producing another daughter product, another radioactive species that's going to cause any problems. In terms of how this works in practice, so the patient would be injected with the tracer molecule. This particular patient is getting a brain scan, so what's happening is that the tracer is injected, it moves through the bloodstream, hopefully goes into the brain, and what happens then is that when the positron is released, it only moves a very short distance before it collides with an electron. And what that does is produces two gamma rays, two photons, at 180 degrees to each other, so in directly opposing directions. And that annihilation process, because of the geometric constraint, that 180 degrees, you can then collect the information, so you can detect the photons through a gamma camera, and then use that to create a three-dimensional image inside the body. And so, Jack, you're going to have to do the job, I'm afraid. So we have, they always say you've got to wear your heart on your sleeve. Well, we're wearing all our organs on our apron tonight. So this is sort of just to mimic this sort of idea. Clearly, this mannequin hasn't been administered with a dose of FDG, but what we can then do is use in this case, a Geiger counter, but something that detects these gamma rays and identify where the molecule has been picked up.
Can you hear that?
Don't know if we can hear it.
Yeah,
can hear it. Okay, so this person is not looking too well. This, just to give the idea of being able to then use that emission and pick up detect it with a gamma camera. A little bit more sophisticated in the lab than said polystyrene, but never mind. So that's broadly the process that's taking place. And an image of this patient has been given a dose of FDG, so that fluorinated glucose. And you can see all the bright areas are where the FDG, the positron emission is occurring. And in fact, you can see it's in the brain up here, obviously in the main organs here. And this particular patient, the problem that the point that they're trying to probe is whether this person has a tumour in the colon. And so that's the situation. So you can obviously see it down here, but in order to pick up that tumour in the colon, you have to administer rather more of the radioisotope than ideally you would like, and certainly not going to be good for detection of early onset disease. And obviously, if you can the earlier you can detect the problem, the better the prospects of a positive outcome. Another development that's happened very recently is the advent of a modification of this technique called total body PET. So on the right-hand side, you can see a sort of typical PET scanner. It would be picking up the brain area only, and so all that really matters is that tracer gets to the brain. But nowadays, and in fact, at this moment in time, Imperial College in London and King's College in London are installing the first total body PET instrument in the UK. It's a £13 million investment from the government. And the idea is that you can get a huge amount more information by being able to do total body PET. To do that, of course, you need tracers that are going to be delivered to particular organs that you can then pick up. So you need many more tracers, and they need to be highly selective, and used in low quantity. So these are some of the challenges that are there and present for researchers an interesting area to work in. So, as we think about developing alternative PET tracers, we want to meet a number of key criteria. Fast and efficient late stage radio labeling, so ideally you're going to introduce your radioisotope right at the final step of the preparation, so that you just need to make sure it's pure and then it can go into the patient. You're not getting significant decay. We would like to be able to administer a radio label, I should say, we'd like to be able to radio label close to room temperature, particularly if you want to connect up a peptide or a biomolecule. These molecules tend to be thermally sensitive and also sensitive to changes in acidity and basicity. So being able to do the radio labeling in water would be advantageous because the fluorine 18 is coming off the cyclotron water. So ideally, again, you can take it directly and use it. And importantly, somewhere in the molecule we want to be able to connect up a biomolecule, a peptide, that's going to act as the delivery vehicle to get the radioisotope to the right part of the body. Again, if we're thinking about total body PET and thinking about using multiple tracers, being able to do this radiochemistry at very, very low concentrations is important. Compared to something like magnetic resonance imaging, even using FDG for PET is much, much lower concentration. But we still need to go lower than that and have that selectivity to tackle this properly. And of course, for these biomolecules, we also want to make sure that we can work in a close to neutral pH, so not too acidic, not too basic, because that's going to affect that peptide. And ultimately, of course, you're going to administer it to a patient. It's going to have to survive physiological conditions, and be at a level of concentration of the tracer molecule that's non-toxic to the patient. We're working at nanomolar concentration. That's a perfectly satisfactory situation. So our interest here became, there are examples of organic molecules I've talked about, but we thought maybe we can think about using molecular inorganic chemistry, use some of the other tools that we have in our periodic table and our knowledge of inorganic chemistry to tackle this. So if we think about non-carbon fluorine 18 compounds, the sorts of things that people have looked at, so just thinking about the bond energy, we want the fluoride to remain bound to the organic molecule, so that bond energy is pretty high for a carbon fluorine. And if you look around in the periodic table, some of the elements close by, so boron also forms a very strong bond to fluorine, and as does silicon. And these have driven new developments in non-carbon based PET imaging agents, and this is some work on a boron fluoride species that can then be radio labeled to put the F18 onto the boron there. And likewise, some silicon chemistry, again using either a silicon chloride bond or even a silicon fluoride bond and swapping it for the fluorine 18 isotope. These are really organic compounds. I mean, it's a bit of a moot point really, but there's a lot of organic material around here, and these also become quite fatty molecules, so they don't dissolve particularly well in physiological conditions. So there's some problems in that respect. But if we think about going to metal complexes and thinking about these complexes that we were talking about earlier, so the scheme at the top here is just trying to, just in a cartoon sense, illustrate the idea. So this is going to be the ligand that's going to wrap around the metal ion and generate our stable fragment. We then got some kind of linker, and then this will be our biomolecule, dangling off the back of the molecule. So in one of the systems that we've been looking at is this one that's rotating on the screen at the bottom. It's got a macrocycle, it's got N3, 3 nitrogens in the ring, and some other pendant groups that can also bind to the metal centre. So that's going to be the bit that binds to the metal. We can then, once we've got the metal bound, we've generated our metal ligand scaffold. It probably isn't going to look like this. There will be something sitting in this site that's vacant down here, but for our purposes, for illustrating, that doesn't really matter. And then at the final stage of the process, we can introduce the fluorinating. And so the key point about these sorts of molecules is that you can do all the assembly, you can put everything together except the F18, and then that goes in at the final stage. And as long as you've got really good stability, then hopefully that's going to serve well. And again, I've just, it doesn't matter too much, but I've got a molecule here that sort of shows that the sort of arrangement of the fluorine at the green fluorine at the top, the macrocycle sitting around the face of the metal, and some pendant groups also coordinating. So that's the sort of idea that we can start to think about. If we have to, we've got lots of metals in the periodic table. So what are the criteria as far as the metals concerned? So we need strong interaction, strong affinity for fluoride. And so that helps us to think about the sorts of metals that might be suitable. We want a good control of the chemistry, so we don't want the number of ligands that are going to bond at any one time to be varying, because that's not controlled. So we want what we would call a fixed coordination number around the fixed number of ligands bound to the metal centre, and also a stable ion. We want fast uptake of fluoride, so we've got to think about the rates in which these reactions are going to take place, and we'll look like that to be at the final stage of the preparation. And of course, as we know, the fluoride has got to remain bound to our metal complex all the way through. So these are the sorts of things that we were thinking about, and we had been doing some chemistry, trying to make silicon fluoride compounds for a completely different project. We made some molecules, some of them were horribly moisture sensitive, they didn't work for the project that we were interested in, but we noticed that one of the macrocyclic complexes that we had made with silicon fluoride was incredibly stable in water. And we could dissolve it in water and leave it for weeks or months, and it didn't degrade at all. And so if we start thinking about that's kind of what got us thinking about using metal complexes actually. So here's our fluorine in green up here. We've got pretty much the whole of the periodic table to think about. The metals across here tend to be rather fast in reacting. That's a good thing in some ways, but they don't form terribly stable complexes, so they're kind of not really part of the equation. I keep doing this. These ones down here, the sort of heavier, called heavier transition metal ions, they tend to form very strong bonds, but because of that they react rather slowly, so they're probably not going to be any use. And so we start to think about these transition metals in the first row here, and also maybe some of the main group ions on the right there. And so we've got some metals that we can think about, and then we can think about the strength of the metal fluorine bond. So this slide is just giving some numbers. The numbers don't really matter. All we need to see is that the metal fluoride bond is stronger than the metal chloride bond in all cases, which means we should, if we do a chloride for fluoride exchange, there should be a driving force for that. And so these all look quite promising. But it turns out, if we think about a little bit more of the chemistry, it turns out that some of the transition metals are not so good because they react rather slowly, a bit like the heavier elements that I mentioned a moment ago, or maybe they don't have very stable coordination numbers, so we kind of knock them on the head. But there's a range then that we're left with of metal ions, Lewis acids, that have got the sort of properties that look quite promising. And I'm just going to touch on a few of these just to show you some examples. So these are the ones that are of interest, the aluminium, gallium, indium. and scandium and iron systems, and typically in the 3+ oxidation state. In terms of the macrocycles, I've shown you some examples already, but this N3 framework seems to be really good, this 9-membered ring. In fact, we use, we put this aromatic group, this benzene group, on the backbone of one of the nitrogen atoms, because, well, there are 2 reasons for that. One is that the benzene ring gives us a means of using ultraviolet UV-vis spectroscopy, so ultraviolet visible spectroscopy to track where that molecule is going, and so we can see that in our radio traces. But it also gives us a site to bind a peptide, so bind our biomolecule later in the process. So we've got neutral ligands like these ones here, and we've also got the possibility of putting some pendant arms that are going to act as additional stabilization features. And these metal ligand fragments are kinetically and thermodynamically very stable. So they've got the sorts of characteristics that look really promising. I've already referred to the benzyl group, so that's going to be helpful in terms of that bioconjugation, to be able to target a particular part of the body, particular organs or cells or receptors for detection. So these are the sorts of systems that we're interested in, and we need that stability from the macrocycles, so that's good. And this is some work that has been published, so this is some of the first work in the area from a group in Canada, Bill McBride's group, and you can see there's our N3 macrocycle with our pendant groups and some kind of tether off the back which has got the peptide. And what they were able to do was introduce aluminium to fluorine 18, and these molecules are actually going through clinical trials now for using in the clinic with patients. It's a really versatile system, and it's got a lot of the characteristics that you might be looking for in terms of that bioconjugation and so on. Another example on the top right, and this is relevant to something that we've looked at, the gallium equivalent chemistry. So gallium's just beneath aluminium in the periodic table, and what we find is that the chemistry, as you move in the periodic table, some of the trends are quite predictable in the groups, but the detail is quite different, and that's important in this sort of chemistry. So some of the challenges with these systems is the relatively high temperature required to get the metal ion to the metal fluoride to bind, so 110, 120 degrees. It's a little bit tricky with biomolecules, it's not really desirable. The other problem is the pH. They tend to need to be, I don't know what I'm doing here, sorry. They tend to be require the pH to be very tightly controlled in sort of acidic conditions. And again, that's not going to be ideal. So, really interesting starting point. There are some developments in this chemistry that are addressing some of these problems, but we took a different approach. They've used some open chain non-cyclic ligands to get room temperature labeling, but then you lose something in the stability. We took a different approach, and that was to think about changing the metal ion. And just briefly go through a couple of examples. So we start off with making this molecule in the center here. This is a gallium halide complex, gallium trichloride species, again with this nitrogen macrocycle on the back. So this is a fairly stable molecule. You can prepare it and isolate it and store it. We can then radio label that by, we only need one fluorine 18 atom in the molecule, so we add almost the equivalence of fluorine 19, the standard form of fluoride, and we just dose in a little bit of fluorine 18 directly from the cyclotron in water. And this proceeds really nicely, just about 10 minutes at 80 degrees C, and that you get, uptake of about 65% of the fluorine 18 goes into the molecule, which is pretty good. Just comment on the concentration that we're working on. So this is in the micromolar concentration. We'd like to be able to go down from that. we think we understand why this might be the limit, but that was as far as we could get with that molecule. So we took a slightly different approach. We know the fluoride complexes themselves are really stable, so this time we made the fluorine-19 complex. So this is the standard fluoride that you would have in the lab. And now we're doing an isotope exchange. So we're swapping out the fluorine-19 isotope for the radioisotope, the fluorine-18, the positron-emitting isotope. And again, 10 minutes, 80 degrees C. The reaction also works at room temperature, but it's a little bit slower, as you would imagine. And you get the product on the right. It's the same molecule as we saw a moment ago, but synthesized, radio-labeled in a slightly different way. This time we can get down to sub-30 nanomolar concentration. So that's really encouraging that the molecules are still radio-labeling effectively under these sorts of conditions. So this slide just summarizes some of the attributes of these molecules. We can make them and we can do all the chemistry up until that final step, which is the incorporation of the fluorine-18 and mild conditions and so on. We can also look at some of these negatively charged ligands, so the macrocycle with some pendant groups, and we've looked at a couple of examples. These two molecules here, it's really this one I want to concentrate on. This is a phosphonate derivative, so it's got phosphorus oxygen units here. It's a dianion, so 2- charge on the ligand, and we've got 5 donor atoms, 3 nitrogens and the 2 anionic oxygen. So we're going to use 5 of the binding sites on the metal just to tether to the ligand, and that's going to leave 1 site. So we only need one fluoride ion in the molecule. And we went ahead and made that compound. We can radio label it, or we can make the gallium chloride compound just by reacting with gallium GaCl3. We can see from the spectroscopy that we've got two different phosphorus environments in our spectrum, and that tells us we've got inequivalent phosphorus centers, so it tells us about the geometry of the molecule, but of course all the techniques that we would be using in molecular chemistry anyway. And we can then crystallize that compound, and you can see the 6-coordinate geometry, 5 donors to the macrocycle and 1 fluoride. And when we look at the radiofluorination of this molecule, we can take that chloride compound and just add fluorine-18 in water straight from the cyclotron, and we get good uptake. We generate our molecule here. We can do this with a variety of metals. We've in most detail at gallium-3 and iron-3. And this table just to focus on the right-hand side. What this is showing is that we're getting really pretty encouraging radiochemical yield, so good fluorine-18 uptake. That's only the start of the challenge, of course. We've then got to think about the stability of the molecule in physiological conditions. And so we've done some tests in serum and in buffered solutions that mimic physiological conditions. And the graph here shows the radiochemical purity. So it's really telling us about how quickly the molecule is decaying and liberating F18 over a period of a few hours. Now your patient's not going to be in too good shape. If you can see in the phosphate buffered saline that after an hour we've liberated all of the fluoride. So nice idea, but doesn't work in terms of going forward. But if you go to the gallium compound, you can see at the top here in black and red, the black is in an ethanol water mixture, just looking at that radiochemical purity, and the red is in physiological conditions. And you can see much better, over 95% retention of the F18 over, in this case, 4 hours. So that's a really encouraging result. And clearly there's much work to be done in this area to take this forward. But I hope that I've been able to show you some of the developments in using metal coordination chemistry towards a different application, an area that these sorts of molecules haven't really been used before. You can see that the gallium compounds and the aluminium that I showed you have encouraging characteristics, and they look promising for future development and implementation. The aluminium are most advanced in that sense, and it'll be really interesting to see over the next year or so the results of these clinical trials as you move through. In terms of what we're doing, obviously thinking about putting this biolinker into our gallium species to be able to target the various receptor sites for specific targeting. Just to comment on some of the subtle properties. So this is the molecule on the left here has got these carboxylate type groups. The molecule that we're looking at has got phosphonate groups bound to the metal center. We made the gallium complex of this species, and we can radio label it, but it's not stable at all. The one on the right that I showed you has good stability over several hours. And the reason we think is that the bond lengths around this ring here, the ring that's highlighted, the bond lengths mean that the angle at the metal center is a little bit closer to the ideal 90-degree angle in a regular octahedron. And so that's increasing the stability of the molecule. So it's a quite subtle effect, but it makes a big difference in terms of the stability of the molecule in practice. So with that, I will just conclude with a few comments about the complexes. I think we've talked about where the work's got to and where it's going, and we're not the only people working in this area, of course. It's an area that's become quite popular, a number of groups around the world. But for us, it's about putting the conjugating groups on and really testing these now in the biology side of things. But maybe more important, just to take a step back from the specifics of the chemistry. I guess I wanted to say, I think molecular inorganic coordination chemistry is an important area of chemistry where there is still huge amount to discover. Lots of new molecules emerging. Sometimes you don't know when you make a molecule, you don't know what its properties are going to be, and sometimes there are surprises. I would always encourage young people in the labs and studying chemistry to keep their eyes open for unusual things, because unusual things can lead to new opportunities. And that's we're chemists at the end of the day. We work with molecules, and there's lots of interesting stuff there. And some of these molecules will find real life applications in the fullness of time. For me, working with researchers in other disciplines has been something I've really enjoyed in my career. It always challenges you because physicists speak a different language from chemists, from biologists, and so on. But once you get over these bits, the conversations and the challenges, you can start to look at interesting areas of science that sort of sit at the interface of the different disciplines. And I think that's a really interesting place to be, that people bring along their expert skills in their own area, but collectively you can do things that no one researcher can do on their own. And so, the world's changed a lot over the years. We've got techniques and instruments and so on that we couldn't have dreamt of a few decades ago. And I really do think it's an exciting time to be studying science and doing chemistry. And for me, it's a hugely creative discipline. I think there are great prospects for new innovations, and for sure, many of the developments that are coming from chemistry will feed into tackling some of the global challenges that we spoke about earlier. With that, thank you very much indeed for your attention, and I'm very happy to take any questions. Thank you.